So we'll go directly to the presentation. Okay, I think that's a bit better. So we can get a larger real estate. So in the last class, we said that the chopper stabilized amplifier has three modules: the modulator, the AC amplifier, and then the demodulator. And we said that a good AC amplifier is it's an instrumentation amplifier. An instrumentation amplifier suggests the internal circuitry is just the same as that of an op-amp, but all they do is use very high quality components, very low noise components. So I gave you the circuit diagram of a typical op-amp made by Texas Instruments. And if you look at the circuit, it can actually be divided into three blocks. The first block is where the inverting and non-inverting circuit is. And in this one of ours, it ends at Q5 and Q6. So that's the first stage. Now the middle stage, in this case, we just comprise of Q8, Q10, Q11. This is actually just for biasing. Just for biasing using current mirrors. So just a biasing circuit. And then Q15, Q16 is the Darlington for the second stage, which have an active load. The load is actually Q13. The load is Q13, and the inputs to Q14 and the Q20, which are actually class B output stage. Q15 we said was just for protection. Now, if you want to convert this to an instrumentation amplifier, you got to ensure that Q1, Q2 are very well matched. Q1, Q2, in fact, Q3, Q4 also very well matched. Q5, Q6, very well matched. And all these are low noise because any noise generated in the first stage will be amplified by the second stage, which comprise of Q15 and Q16. The gain of the output stage is just less than unity because it's just emitter followers. And then, of course, the other thing we've got to ensure is that all the resistances used inside the circuits, all resistances generate noise. Remember, the noise generated by a resistance, V noise RMS is root 4 KTBR. There's the thermal noise generated by the resistance. T is temperature in Kelvin, B is the bandwidth, R is the resistance in ohms. And different resistances tend to generate different types of noises. So normally metal oxide resistances are the lowest noise resistances. So all this will be fabricated into an IC chip. Now in the notes I've given, I've posted for you this circuit and its data sheet in Google Classroom. But here I've just sniped it and put it inside my notes over here so that I don't have to refer to those data sheets, which we saw last time. So summarize some of the typical characteristics of a 741 at 25 degrees centigrade. Remember that even 741s, there are different grades of them. And different companies make different grades of 741s. There are some which are for the do-it-yourself market. There are some which are for the commercial market or industrial market. There are some which are for like the military. So those ones should be able to work what the temperatures are very, very hazardous, say like in Greenland or in the poles or in Antarctica, and also in places like Sahara Desert. So the different qualities, different prices. But here I've just given a typical one like the ones we use in the labs. So typical input offset voltages. So these are the input offset voltages referred to the input is about 5 millivolts. Input offset currents, that's the current required to balance the op amp. Means in this top circuit over here, if I ground pin number 3, the input, non-inverting input the ground, and the ground pin number 2 to the ground, and then monitor the output voltage with respect to the zero reference. If it is not zero, and I supply one of the inputs to the constant current source until the output becomes zero, that's referred to as the input offset current. So it's the current required to balance the output voltage to become zero. Then the typical bias currents over there, 100 nanoamperes, means for proper operation of the op amp, at least a current of approximately, that's 0.1 milliamps should flow through the inputs pin number 3 and pin number 3 and pin number 2. And there's a common mode rejection ratio, which should be as high as possible. So if you got 2 inputs, of some magnitude, if you feed them to the 2 inputs, ideally the output should be 0 for common mode signals. That's a rejection ratio of infinity, but in practice, we get a ratio of about 100 dB. Then we have the power supply rejection ratio, typically of about 20 microvolts per volt. That tells you how well the power supply, when it changes, it interferes with the output. Now, I won't waste time going through all of this. We talked about IO drift, VO drift, and this is supposed to be the slew rate. I've spelled it wrongly. It's supposed to be slew rate, which is what we ended with in the last class. And I said that the slew rate is determined by this capacitor C1. Remember, there's a current over here, there's a current over here, which is driving this input over here. So this current, let's assume it's, of course, it will be it's a sinusoidal current. Okay, but let's assume it's IRMS. Let's call it, say, IN. Its value is IN. Then this current is supposed to be driving Q5 and Q6. But as the frequency increases, the current can actually pass through this capacitor, the C1. Now the current through C1, IC1, is equal to C dV naught dt. I'm using V naught because the voltage at this point over here is just the same as the voltage at the output over here. It's slightly less. If we call this voltage, say V naught, this voltage will be V naught also. The AC voltage, of course, the bias voltage for proper operation of the circuit, the base of Q14 should be slightly higher than the base of, than the emitter of Q14 for biasing purposes, maybe 0.5 volts between the two. But the AC varying because the voltage gain of the output stage, which is emitter follower, is just maybe 0.99 something, okay? Because it's a buffer stage, it's just a buffer stage. All it does is to increase the current drive. That's what the class B output stage does. It doesn't have a voltage gain. What it does, it increases the current gain. We approximated the beta of the transistors, in this case Q14 and Q20. So the voltage at the other end of the capacitor C1 is approximately equal to V naught. So when this current IC1 is equal to N, then we say that is the slew rate limit. The slew rate limit of your amplifier system. So actually you can calculate it. So if we say V naught of T is equal to, say, some A cos omega T, then dV naught of T will be equal to A omega sin omega T. So you can get the magnitude, just substitute this function for that. So you'll get C A omega T, A omega sin omega T is equal to IN. And when sin omega T is maximum, then this term here, sin omega T is equal to 1. Or let me just leave it simply that the slew rate is just obtained from this equation. is just obtained from that equation. C dV COT dt is equal to IN. Or dV COT, which is the same as d naught dt is equal to IN divided by C. So you can increase the slew rate by making C as small as possible. Remember, C also provides some feedback. It also provides some feedback between the output and the input. So you got to be very careful so that it doesn't provide positive feedback and therefore interfere with the stability of your amplifier. But just in short, that capacitor C1 determines the rate at which the output voltage can change. When IN is equal to the current passing through C1, then we say op-amp has reached its maximum rate of change of the output, which we call the slew rate. Okay, today I didn't want to spend a lot of time on this one, on the amplifier, because we've got to move on. But these characteristics, I'm sure when you study the op-amps, you should know all of them. So slew rate, I've just emphasized on slew rate because it's an important thing. So you see, like this one is 1 volt per microsecond. Okay, so that means dVc sorry, this means that dV naught dt is 1 microsecond maximum. So that's the maximum rate of change that the op-amp can have. And as I said, that's determined by the value of C1. And of course, there's the unity power gain, which is the frequency at which the gain is 1. Then there's the full power bandwidth, which is, in this case, is 50 kilohertz. That's if you have to plot, supposing you need to plot frequency, and this is the power output, you get a curve like that. So this frequency, when the power output falls by minus 3 dB, or power falls by half, or output voltage falls by √2, it's referred to the full power bandwidth. It's referred to as the full power bandwidth. Even that one is a function of the slew rate. Okay, then the open loop gain, AD, 100,000, depends on the op-amp. Then the open loop output resistance, I mean this resistance seen looking back, the resistance seen looking back at the output, the resistance seen looking back at the output, maybe for it's typically maybe 100 ohms open loop input resistance as the resistance seen at the input of this circuit over here. Could be 1 mega ohm, it depends on the design. So like this one, they're using Q1 as an emitter follower to increase the resistance, driving a common base circuit formed by Q3. Depends on the design. For example, if the first transistor, that Q1, instead of using a BJT, we use an FET, then the input resistance can be increased to 10 to the power 12. So if the load, if your driving source has got a high impedance, you want to transfer most of the power from your source to the input of your amplifier, then using maximum power transfer theorem, the two resistance should be the same. But when we are concerned with voltage amplification, we just want that the resistance at the input the amplifier should be much, much greater than the resistance of your source, so that most of the voltage will appear at the input of your amplifier. So if your source resistance is high, you need an amplifier with the high input resistance. So you can use a JFET input or a MOSFET input. Okay, so let's consider the block diagram. This is a block diagram of a chopper stabilized amplifier. The page has shifted because I put some things which are not there before. So this is how it looks like, the complete amplifier system. Your modulator, your AC amplifier, your demodulator. Then you have your oscillator, which drives the square waves. So these outputs are in synchronism. So if this one goes high, this one should also go high. If it goes low, they should also go low. So that's a typical block diagram of a chopper stabilized amplifier. Okay, so I've written here, the above diagram represents a complete chopper DC amplifier. They're referred to as DC amplifiers because they can amplify voltages which vary very slowly with respect to time, which may be regarded as a carrier system. It may be regarded as a carrier system. Now, the term carrier is analogous to what we use in telecoms to transport information from one point to the other, normally using a sinusoidal waveform. Of course, in this case, we are using rectangular waveforms. But remember, using a Fourier transform, a rectangular waveform can be split into its harmonics, which are pure sinusoids. Okay, so this may be regarded as a carrier system where the chopping frequency corresponds to the carrier frequency, while the small varying DC corresponds to, so here I've done a mistake over here, corresponds to, actually I'd edited this, I've opened another of my notes, corresponds to the, I'll call it the information, corresponds to the information signal. Okay, so in a carrier signal from your telecoms, the information signal maybe you're calling it MT, and then this oscillator could have maybe some amplitudes. So we'll demonstrate this theory using this carrier analogy to implement a chopper stabilized amplifier. So I'll do it with the equation over here. Question: demonstrate with aid of analysis that the circuit below can be used to implement a carrier-based chopper amplifier. Then next, find the gain of the chopper stabilized amplifier system, and then explain how to recover the amplified signal. So this is our carrier-based system. Now in a carrier-based system, it's just identical to this typical block diagram on top over here, which we studied before. So this is our carrier-based system. So the carrier-based system, your oscillator is normally a sinusoidal oscillator. Okay. And the modulator we are going to use is a multiplier. So the modulator over here is just a multiplier. So it will be a DSB multiplier. So this will just be a multiplier. Okay, and then we can have this oscillator producing maybe a signal which is A cos omega CT. And the signal here also will be A cos omega CT. So C omega is frequency in radians per second. C is, this stands for that carrier frequency. Okay, then you're told to obtain the spectrum of the signal at the output of your modulator. You should read comma. It should be a modulator, comma, AC amplifier, and the modulator. So my signal would be M of t. Okay. So if in the frequency domain, I'll just draw a spectrum over here for M of t. So let's assume this is the highest frequency. This is our signal, M of t. So this is omega. So this is the maximum frequency. And this side is amplitude, of course. So this is the spectrum of M of t, or the Fourier transform of M of t. Let's assume it's like that. So it's from 0 hertz. Instead of confusing with omega, let's just use frequency. To F, let's call it FM. M to denote it's our information signal. FM max. So this signal has got a spectrum from 0 hertz. This axis now will be in hertz. Okay. And our carrier is A cos omega CT. So it's a pure sine wave. So the spectrum of our carrier frequency, its amplitude is, so for M of t, the amplitude is just 1. And this one, the amplitude is A. So this frequency is omega c. Remember, omega c is 2 by fc. So if you use this diagram on top over here, so our modulator is just essentially a multiplier. It's going to multiply the two signals. So in the time domain, the output at A will be this first equation over here. Let me call it equation 1. And this will be equation 1b, say. Just put the A outside. So that is the signal in the time domain at point A, and at point B, we'll assume that the reactance, the capacitances are 0. Remember, these are capacitance C1, and they normally just see C and C some values. So we'll assume that for proper design, the reactance of this capacitance are almost equal to 0. And our amplifier has got a gain, which is say equal to K. Our AC amplifiers are gain equal to K. So at point B, the signal at A is multiplied by a scalar K. So you'll get this equation 2 over here. You'll get that equation 2 over there. And then at point C, so 2 and 2b just the same thing. We just put the A outside. And then at point C, oh, this thing went to the next page. So at point C, which is actually our output over here, the signal at B is multiplied by A cos C omega t. So And point C is this, the first part of the equation. This was our signal at B. This was at B. And then we multiply it by this. Odera, Titus, please switch off your mic. So I think we reached this equation. Let's call this equation 3. So if you multiply cos omega ct times cos omega ct, you can just substitute it by this term over here. This cos, it will be cos squared omega ct, which is 1/2 into 1 plus cos squared omega ct. You can use the identity. Just use the identity cos A plus B. Then use cos A. Sorry. Cos A minus B. Then you rearrange it. You'll be able to solve for cos squared omega ct. You just put A equals to B. Just using the identity. So there we just put the identity directly. That cos squared omega ct can be written as 1/2 into brackets 1 plus cos squared omega ct. So I'll substitute that term back. Let's call this one 4. So here I've just substituted 4 in 3. You substitute 4 in 3, you'll get that term. So then you multiply the outside bracket into 1 plus cos squared omega ct. Then you'll get 2 terms. The first term is a squared kmt divided by 2. The second term is a squared kmt divided by 2 into cos squared omega t. So it means that if you had to look at the spectrum of the output, if you had to get the Fourier transform of this one, you're getting a double frequency term at actually twice omega.
Excuse sir.
Yes.
I think the term in the bracket should be 1 cos 2 omega ct, not cos squared omega t ct.
I don't know, mistake, eh? Okay, let's do it. From first principle for everybody. You know, also do mistakes sometimes typing. Why does, where is Rab now? Okay. Okay. Cos A plus B is cos A, cos B minus, I don't remember these things, I just use them from first principles. And then cos A minus B, the same as cos A, cos B, minus sine A, sine of minus B. So this one will become positive if we remove this one. And therefore, if we add, call that equation A, B. So if we add A plus B, we'll get cos A plus B plus cos A minus B is equal to 2 cos A cos B. And if A equals to B, let's assume they're all equal to A, then we get cos 2A plus 1, because this is equal to 0, is equal to cos squared A. And therefore, cos squared A is 1/2 1 plus cos 2A. Okay, in fact, I saw I was getting the problem because I needed to look for the double frequency. So you're correct. So if A is omega, so this tells me that cos squared omega is 1/2 1 plus cos 2 omega. Okay, so let's go back to my equations here where I have done the mistake. Yeah, it's this equation 4 over here. Is equation 4 over here. I think it was typed wrongly. And the same with this one. No, I don't want the okay, thank you. This one, because in the frequency spectrum, I was going to get a problem because 2 okay. Thank you. Because I was going to get into problems when I was getting the Fourier transform. Okay. Okay, so thank you. So if you're to get the Fourier transform of V naught, then we'll get the first term over here, which is A squared KMT 2. So this will be our original spectrum starting from 0. But the amplitude now will be A squared K divided by 2. And this amplitude over here will be A squared K divided by 2. So this is our baseband signal. And then around 2 omega. So if this is 2 omega C, you're going to get a spectrum like that. And 2 omega. So in order to extract our original signal, this is axis. So this is your omega axis. y-axis is your amplitude. So here I've written that the overall gain of the chopper stabilized amplifier system is a squared k divided by 2. And to obtain the output from the chopper stabilized amplifier system, a low pass filter whose cutoff frequency is slightly greater than the highest frequency component of MT must be employed at the output. Then the recovered signal is given by, now because of this typing, everything has gone haywire here. Is given by a squared k divided by 2 MT. And this is just an abbreviation. So to recover the signal, you're going to put a low pass filter whose response is maybe something like that. So this is the response of the low pass filter. To recover back our baseband signal. So it should be able to pass the highest frequency component of our baseband signal. The important thing to note is that the above implementation, in the carrier-based implementation, illustrates the principle of the operation of the chopper stabilized amplifier, but in practice, the analog modulator and demodulator have to be designed properly to minimize drift problems inherent in the multiplier implementations. So basically, that's all we are saying here is that the modulator we are using here, and also the demodulator we are using here, they themselves should not add drift voltages. I know in telecoms, you people are just, for a multiplier, you just put a circle with an X inside the middle, and you say you're multiplying the signal. But in electronics now, you got to remember in your telecoms, maybe you're just putting an X, and then you got one signal here, another signal here, and then you say the output is there. Okay. But in electronics now, we are the people to design this multiplier. We are the people to design this multiplier and see if that multiplier itself has got its own drift problems, which will add to our signal and therefore give rise to errors. So that's the meaning of the last statement of this implementation over here. The implementation using a carrier-based system. Now, the other type of implementation, which I'm calling number 2 over here, is an implementation of a chopper stabilized amplifier using a positive gain, negative gain amplifier. So in other words, we are going to be using a modulator which is a positive gain and a demodulator which is a negative gain amplifier. So here is one of the modulators over here. So let's see, you people are supposed to be experts with using op-amps because you are drawing them as a triangle with a positive input, negative input, and an output. So let's see that this implementation, why this implementation is called a positive gain, negative gain amplifier. So here we've got an FET switch. So this FET just acts as a switch. So we can represent it maybe this way. So you have a diode at the input such that the voltage does not go so much positive. It's like close to zero. When the signal, remember, the signal over here, the control signal normally will be the negative will be minus Vp. And this should be as close, the positive side should be as close to zero as possible. Vp is actually the pinch-off voltage of the FET. So our control voltage, when it goes positive, it will be clamped by this diode. It can't go more than the forward bias of the diode. So if you use a germanium diode, that will be approximately 0.1 volts. So the maximum positive will go is about 0.1 volt. The maximum negative it can go with respect to the earth over there is minus Vp, which is the voltage required to turn the MOSFET off. Now, in the last class, I gave you some data of some chopper stabilized, some chopper FETs, and we saw it was the voltage required to switch it off was ranging from maybe 0.3 volts, minus 0.3 volts to maybe minus 4 volts. Okay, they vary depending on the manufacturer. So just make sure your control voltage that you'll be using to open and close this switch opens the switch and also closes the switch. So this is a simple implementation. So let's see the output. Now from this circuit, can somebody tell me how we get the output? Remember, the switch will just open and close. So when the switch is open, it means the point between R6 and R7 is open. When the switch is closed, the point in between R6 and R7 are connected to the earth. So actually, we can get an equivalent circuit, which I've drawn over here. Okay, to put some, and this I just added today, I put some characteristic curves of an N-channel FET. So, for example, for this one, when VGS is 0, the maximum current flows. As you start decreasing the current, when I see the current drops, but to completely switch off the FET, you got to know the voltage required to switch off the FET. So for this one, it will be much, much more than this minus 3 volts, because minus 3 volts here, the drain current is still flowing. I just put this one just to remind you, if you had forgotten the characteristics of an FET, an N-channel FET. Okay, so let's come back to our problem here. So when switch S is closed, our circuit becomes like this first diagram on the left over here. When switch S is closed, it's like this. These 2 points between R6 and R7 are connected to the earth. So if they're connected to the earth, we can split R6 connected to the earth, R7 connected to the earth, so you can get this circuit over here. Now, once you get this circuit, this is our simple non-inverting amplifier. So long as the source of my information signal, VMT, the resistance, which is much, much lower than R6, then this is just your inverting amplifier. For your inverting amplifier, normally the resistance between the output and inverting input, we normally call it RF, or your feedback resistance. And this resistance, the first resistance, we normally call it RI. So for your inverting amplifier, V0 is just equal to minus RF over RI into VI, but RF is equal to RI. So we can write that V0 is just minus VMT. So when switch is open, the equivalent circuit is, what did I write? sorry. So this one, because of the editing I did today, a lot of my things are been misplaced. Let me try and And there's no time to edit right now. So this one should have come here. Okay, I'll put it here. Okay, so when it's case 1, switch S was closed. Now case 2, switch S is open. So this is the circuit with this. Switch S is open. So this midpoint between R6 and R7 is open. So next, let's get at what is the output voltage when this open. So when it's open, we can actually draw two equivalent circuits. We can actually draw two equivalent circuits for this. So I've just done it here. Let's see. So what I'm going to do, I'm just going to put two sources. VMT going to the top, going to the resistance R. Another VMT going to the resistance R6. Wow, 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 wow. Where did this diagram go? Did I miss it? Let me do it by hand instead of, let's come back here and do it by hand. It's much faster. Okay, so to solve this circuit over here, this circuit is just equivalent to in fact, even that, I've taken a step ahead. I've taken a step ahead. Do you have class after this? Do you have class after this, CR?
Yes.
Oh, okay, let's do this one quickly. So to solve this one, the first step is just to so this circuit over here, when the switch is open, you can split the supply into two, and you get VMTs with respect to the earth. So this is still the same circuit where this is R6, this is R7. Okay, so you get V0. So it's like having an amplifier with two inputs, one connected to the inverting input, one connected to the non-inverting input. Now to get the response, the overall response to this amplifier, because the amplifier is being operated in this linear region, the output is the sum of the responses due to the signal connected to the inverting input with the signal connected to the positive input equal to 0, plus the output due to the signal connected to the non-inverting input equal to 0, and the signal connected to R6 and R7 equal to VMT. Ogola. Ogola, why are you putting music for us? Okay, since time is up, go and try it. So the response, I'll call it V0, will be equal to V01 plus V02. So V01 is a function of the signal connected to the inverting input only. I'll call it U1. And the next output is the signal connected to, I'll call it U2, the positive input. So that's how we get the overall response. So I've done it in the notes, but we can continue with it in the next class. Okay, thank you. So if there's any questions, you can ask. Any questions you can ask? Okay, we'll stop over there. So we'll do it in the next class.